In this lecture, we will discuss about the types of power in electrical systems, which are the apparent power, active power, and reactive power. So, apparent power. As far as the apparent power is concerned, the apparent power is actually the total power of the electrical circuit, or you can say this is the power which is present in the circuit. Electric circuit. This power is basically delivered by the source to load, or we can also say that this power is generated by or produced by the source. Source here means the AC source. Now let us consider an AC source which is connected to a load, and this AC source is V is equal to Vm sin theta. If capital V is the RMS value of this voltage and capital I is the RMS value of this current, then the source power is basically given by the product of the RMS value of source voltage and source current. So this is the mathematical equation for the apparent power. This power is also known as source power or total power or apparent power, which is already written in this slide. Now, because the voltage is measured in volts and current is measured in amperes, so the unit of S, that is apparent power, is volt amperes, that is VA. So all the AC sources are basically have their power rating in terms of volt amperes. So this is the power which is generated, which is produced, which is delivered, transmitted from source to load. So that means this power will be distributed in the electrical circuit in various forms. Now, if we see, this particular power has two components basically. S has two components, one which we call as the real power and the second we call as the reactive power. Real power is also known as active power or true power. Now this can be understood with the help of a phasor diagram. Now let us see this with the help of a phasor diagram. Now let us consider an inductive circuit in which the current I lags the voltage by some angle which is phi here. This is Greek letter phi. So inductive circuit means not pure inductor. Most of our AC circuits or almost all of our AC components basically or electrical appliances are inductive in nature. For example, your fan, motors, AC, refrigerator, washing machine, cooler, microwave, oven, chimney, etc. Almost all the electrical appliances are inductive in nature. Now, in the last lecture, we studied that in a pure inductor, the current lags the voltage by 90 degree. That is, if you take voltage as the reference phasor, so current will be 90-degree lagging. But this is the case of a pure inductor. However, in our general AC circuits, okay, in general AC circuits, the current does not lag the voltage by 90 degree. However, it lags the voltage by some angle phi, which can be calculated. Now, let us represent this with the help of a phasor diagram. So, let us take the voltage as the reference phasor, and let us say that the current lags the voltage not by 90 degree but by some angle phi. This is the current. Now this current can be resolved in two components. One is, let us say, the component which is coinciding with the voltage, and second component is 90 degree with the voltage phasor. So there are two components. One is I cos phi, which is in phase with V, and there is the second component which is I sin phi, which is 90 degree out of phase with V. So this current has been resolved in these two components. One is I cos phi, and the second is I sin phi. Now, how did we get this I cos phi and I sin phi? This is very simple. We can take it from here. So this is your 90 degree angle. Now this is phi. Now if this is triangle OAB, so this AB, this is base by hypotenuse. This OA by OB is cos phi. So OA is this one, let us say. This is center O. So OA here is OB cos phi, and OB, this is basically your current phasor. So OA is equal to I cos phi. Similarly, the perpendicular component, this one, okay, so you can take it either here or here, that is one and same thing. So this is the perpendicular component, this one, both are same. So similarly, AB by OB is equal to sin phi, or AB is equal to I sin phi. So that is how we have got this current resolved in two components. One is this one, which is in phase with the voltage V. Both are in same phase. And this component is 90 degree lagging the applied voltage V. So now if you see these two diagrams, the same thing is given here also. You have a current, and these two are the components of the current here. Now, if you draw it in form of a triangle, basically, where phi, remember please, phi is basically the phase difference between V and I. Remember this thing. Now, if you draw it in form of a triangle like this, so you will see, and you multiply each of this component with V, multiply this with V, multiply this with V, and then multiply this with V. Now, if you multiply all these components with V, we all know that V into I is basically the volt power. It is the power, and it is basically the apparent power. This is the apparent power. Now, this diagram, this phasor diagram, will be converted into this diagram, which we call as power triangle. This is a power triangle. In this, we have one component, which is V into I into cos phi, means the voltage and I cos phi. This is one thing. Okay, I cos phi is one of the component of this current I. So this is one type of power which we call as true power. V into I is one type of power which we call as apparent power or source power or total power. And V into I into sin phi is another kind of power which we call as reactive power. Now, what is this reactive power? What is this active power? This is the question now. In our previous lecture, we have seen that in a pure resistor, the power is the average power is basically V into I. In a pure inductor, the average power is 0. In a pure capacitor, the average power is again 0. Now, what does it mean? What do we understand by the zero power in case of an inductor and capacitor? And why do we have the power equal to V into I in case of a resistance? This is another question which is associated with the concept of power in electrical systems. Now, let us elaborate this further. So that means our apparent power has two components. One is which is we call as active power or true power. It is one and same thing. And the second is the reactive power, which is this one. Now, active power is always or generally denoted by letter P, which is nothing but the average power. And this reactive power is generally denoted by the letter Q. This thing, if you see this one, this is nothing but a y-axis. If you compare this in terms of axis, basically now you have this is V, which is actually the real axis, and this is your I or Vi sine phi. This is your imaginary axis, and this is your V into I, which is basically the resultant. And then we have Vi cos phi. Now, if you see it in this way, you will understand that Vi cos phi, which is nothing but true power, is the real component of, it is the real component of Vi. Now, what is Vi? Vi is the source power, right? And if you see this one, Vi sine phi, because it is on the vertical axis, y-axis basically, and y-axis is the imaginary axis. So this reactive power is the virtual component of Vi. So these two components are there: active component of the source power, reactive component of the source power or apparent power. Active component is also known as true power or real, and that is why we call it as real power. Now, what is this real power? So let us see this in the next slide. Okay, so before proceeding to the next slide, let us take this one also. Now, if we come back to that axis concept here, so this is the real axis, this is the imaginary axis. Now, this is Vi sine phi, which is the reactive component, and this is your V, and this is your V into I, and then we have Vi cos phi, which is the real component. Now, that means your source power, which is this one, the resultant, can also be expressed in terms of the complex number. That means active power, which is the real part, and the reactive power, which is the imaginary component. So we can represent this as S is equal to P plus JQ. So this is a complex number. That means S is a complex quantity. Now let us go to the next thing, that is true power. And true power is basically the real power of the electrical system which is actually consumed in the circuit. Now, a pure inductor has zero average power. Pure inductor and capacitor both. Now this means that these two components do not consume the power in the electrical circuit. Then what they do with their power, that we will understand in the next slides. So true power in the AC circuit is that electrical power which is actually consumed. The working of your fan, the working of your motor, the dissipation of the heat in the electrical system, the working of heater, TV, refrigerator, microwave is because of the true power. And that is why this power is also known as active power. Now it is expressed as the product of the voltage, which is the RMS value, and the component of the total current in phase with the voltage, and that component is I cos phi. So if we see that phasor diagram once again, so that phasor diagram is this one. This is V, and then we have Vi cos phi, and then we have Vi, which is the resultant, and then we have Vi sin phi, and this is phi phase angle. Now, this is what we call as real or true or active power. So that means we have multiplied V with I cos phi to get the active power. Now, because this power is dissipated or absorbed, it is measured in watts. So the unit of this power is watts. So let us elaborate this further. So true power is basically the RMS value of voltage, the supply voltage, and the components of the total current which is in phase with the voltage, and this component is I cos phi. So it is given by V into I cos phi, and true power is equal to this one, and it is always measured in watts because this power is dissipated, used, utilized. The true power is the useful component of the apparent power. Now, why do we call it as useful component? What does it mean? It means that this power is actually utilized by the electric circuit. The component I cos phi is also called as in phase component or wattful component. Now, why do we call it as in phase component? Because this component is in phase with the applied voltage. Okay, so you can draw it in terms of phasor also. If this is V, then your I cos phi is this one. So both are in phase. Now, as I mentioned earlier also that this power is actually responsible for the torque in motor, supply heat, light, etc. So whatever electrical appliance, whichever electrical appliance is working, that is working because of the true power. It is this power which is responsible for the functioning of the electrical system, and because this power is being utilized, used or absorbed by the electrical components, so this power cannot be recovered. You cannot recover this one, right? So let us come to the next slide, which is related to reactive power. Now, there is a power. Now, when your source delivers power to the load, so if it delivers power, this load does not use 100% of VI. It does not use 100% of VI. So that means it will use cosine phi of Vi, and this is what P is equal to. So the used power is cos phi of Vi. So cos phi can be maximum equal to 1 when phi is equal to 0 degrees, right? And this is the ideal condition. Generally, cos phi is less than 1. This means that the power used by the electric circuit is less than 100%. So now the question is where the unused power has gone. This is the question here. Now that unused power, which is neither consumed nor it is used for any purposeful work, is called as reactive power. This power is actually stored in the electric circuits by the inductor and or capacitor. So we have inductors and capacitor in the electrical systems, electrical circuits. More or less, our electrical systems are made up of the combination of these three components, R, L, and C. These three components are more or less involved or included in the electrical systems. So these two components, inductor and capacitor, they do not dissipate the electrical power. Rather, they store the electrical power because it is their characteristic. Inductor stores electrical current in form of magnetic energy, and capacitor stores electrical current in form of electrostatic field. So when they store the electric current and they have certain voltage or EMF over them, so they store the power also, and that stored power is known as reactive power. It is given by the product of the voltage, which is the RMS value, and the component of total current, which is 90 degree out of phase with the voltage, and that current was, it was I sin phi. So if you come to the same concept, the phasor diagram, current is lagging the voltage by 5 degrees. Current is resolved in two components, I sin phi and then you have I cos phi. So the product of this and this component, that is V into I sin phi, is the reactive power, which is denoted by letter Q. So reactive power is given by Vi sin phi. This is the mathematical formula for reactive power, and it is measured in volt ampere reactive. Now, because V is measured in volts, I is measured in amperes, and this is the reactive power. So just to distinguish between the apparent power, which has the unit of volt ampere, and the active power, which is measured in volts, we have the unit of reactive power as VAR, volt ampere reactive. So further, the current and voltage in L or C, because if we talk about the current and voltage in case of inductor and capacitor, both are 90 degree out of phase. For example, in a pure inductor, we have the voltage leading the current by 90 degree. In a pure capacitor, we have the current leading the voltage by 90 degrees. So that means we have the phase difference of 90 degree in both of these components. And when we have this phase difference, which is 90 degree, because of this 90 degree, we have the reactive power in these two components, L and C. So that means an inductor or capacitor, let it be an inductor or let it be a capacitor, when they are connected to some AC source, so they will not dissipate, both of them. These will not absorb the source power, and because they will not absorb the source power, so average power here is zero. It is zero, right? So this I sin phi is also known as a reactive component or wattless component. Why do we call it as wattless component? Because it is not dissipated, and that is why it is wattless component. And this component is not responsible for the functioning of the electrical systems. Rather, it is oscillating. The reactive power actually oscillates between source and load. So it keeps on oscillating to and fro in both the direction, the AC circuit. Now let us take the summary here. Whatever we have discussed has been summarized here. The power is basically of three types. One is the apparent power, which is generated by the or produced by the source to load, and it is also known as total power, and it is measured in volt amperes, which is given by S is equal to V into I. Then you have active power, which is one of the component of the apparent power, which is the real component. Now, when I'm writing VI, I mean to say the apparent power. Similarly, we have the reactive power, which is the stored power basically not consumed by the circuit, and it is measured in volt ampere reactive. Now, this is the virtual power or imaginary power because it is the imaginary component of the electric power, the source power. So the total power, apparent power is given by S is equal to P plus JQ, and the magnitude can be obtained like this. Now, we can also see the summary of the components. As far as the resistor is concerned, the power associated with the resistor is the active power, which is Vi cos phi, and resistor has zero reactive power. That means a resistor does not store the power, rather it dissipates it. Similarly, an inductor and capacitor have the reactive power associated with them, which is given by Vi sin phi. And inductor and capacitor, they do not have the active power. That means they do not dissipate the power, they do not absorb the power, they do not use the power. This is what we call as the power triangle. Here you can see this is the resultant. Basically the same thing which we seen previously has been shown here just to make you understand. Okay, so this is the vertical axis, so it is your imaginary component, and this is your x-axis, so it is the real component. So power factor is cos phi. This we will discuss in our further lectures in detail what is power factor. So P is S cos phi, Q is S sin phi, and the resultant is here. So this is what the power associated with the electrical systems is. So thank you so much.